Good morning, students. In today's lecture, we will discuss about Artinian modules. So first of all, we define an Artinian module. Let us take an R module M. We say that this module M is Artinian if every descending chain of some modules of M becomes stationary after a finite number of steps. It means if we take any descending chain of some modules of M, suppose we take the chain M1 contains M2, M2 contains M3 and so on. Here these M1, M2, M3, all these are the sum modules of M. So for this descending chain of sum modules, if there exists a positive integer k such that starting from mk, all the other submodules of M, they becomes same as mk. Means mk is same as mk plus 1, mk plus 1 is same as mk plus 2 and so on. So in general we can say that mk is same as mk plus I for every I greater than or equal to 0. Thus, the chain becomes stationary after a finite number of steps. So, if this condition is satisfied, we say that the module M is Artinian module. And we know that if a descending chain of some modules becomes stationary after finite number of steps, then we say that the module has descending chain conditions. So, if M is Artinian module, then we say that M has descending chain condition on its submodules. Now, next we define finitely co-generated module. Let us take an R module M. We say that M is finitely co-generated if for every non-empty family of submodules of M having 0 intersection. Here M lambda belongs to index set. This is a collection which is non-empty family of submodules of M, and the intersection of members of this family is 0 module. Then if this condition implies that the intersection of finitely many submodules of M that is 0, means there exists a finite subfamily from this family having the 0 intersection, then we say that the module M is finitely co-generated module. Now next we discuss equivalent conditions related to Artinian modules. Let us take ambient R module. Then we prove that the following conditions are equivalent conditions. First condition is M is Artinian module. Second, every non-empty family of some modules of M has a minimal element. Third condition, every factor module of M is finitely co-generated. We have to prove that condition 1 implies condition 2, condition 2 implies condition 3, and the condition 3 implies the condition 1. So first of all, let us prove the condition 1 implies condition 2. In the first condition, we are given that module M is Artinian module. And we have to prove that every non-empty family of some modules of M has a minimal element. So let us take F be non-empty family of some modules of M. Now because the family is non-empty, so we can take some module M1 belonging to this family. Now either this M1 will be the minimal, or if it is not minimal, then there will exist some M2 belonging to the family such that M1 will properly contain M2. Now again there are two possibilities, either M2 will be minimal, and if it is not minimal, there will exist M3 belonging to the family F such that M2 properly contains M3. Now if the family F has no minimal element, then what will happen? We will get an infinite properly descending chain of some modules of M, which is given by M1 properly contains M2, M2 properly contains M3, and so on. But this is a contradiction because we are given M is Artinian. So the family F must have a minimal element. Now, let us prove condition 2 implies condition 3. In the second condition, we are given that every non-empty family of some modules of M has a minimal element. And we are to prove that every factor module of M is finitely co-generated. So, to get a factor module, let us consider N is a sum module of M. So we can consider the factor module M by N. Now, we are to prove that this factor module is finitely co-generated. So let us consider a non-empty family of some modules of this factor module. This non-empty family we have denoted by M lambda upon N. Here lambda belongs to the index set. This is a collection of some modules of factor module M by N. Now, let us take the intersection of members from this family, that is 0 of M by N. The 0 factor module M by N, that is N. So, from here we can say that intersection of M lambdas, where lambda belongs to the index set, that is N. Now, let us take tau is the collection of all these M lambdas, where lambda belongs to the index set. And tau dash is a collection consisting of all those some modules of M which are finite intersections of members of tau. Then this family is non-empty family of some modules of M. Now, we are given that every non-empty family of some modules of M has a minimal element. So, by the given hypothesis, this family tau dash will have a minimal element. Let us take this minimal element is A. Now, A belongs to the family tau dash. So, by definition, A will be finite intersection of members of tau. So, they will exist indexes lambda 1, lambda 2, lambda 3 and so on up to lambda n belonging to the index set such that A can be written as intersection of M lambda i's, where I varies from 1 to n. Now let us take an arbitrary index lambda belonging to the index set and we find A intersection M lambda. Now A is M lambda 1 intersection M lambda 2 intersection M lambda 3 and so on up to intersection M lambda n. This is A. So A intersection M lambda. This is again a finite intersection of the members of tau. So that will belong to tau dash. And also this intersection is contained in A. Now we have taken A to be the minimal element of the family tau dash because this is minimal. So by definition of minimal, we can say that A intersection M lambda will be same as A. And this is true for every lambda belonging to the index set. And if intersection of A with M lambda is A, then A must be contained in M lambda. And because this is true for every lambda belonging to the index set, so A will be contained in intersection of M lambdas. Here lambda belongs to index set. Now we have already taken intersection M lambda, that is N. So A is contained in N. Now N is the intersection of M lambdas, where lambda belongs to index set. And this intersection is contained in intersection M lambda i's, I varies from 1 to n. This is A. So n is contained in A is contained in n. So from 1 and 2, we can say that A is same as n. Now A is intersection m lambda i's, I varies from 1 to n. So we have proved intersection m lambda i's, I varies from 1 to n is equal to n. So we can say that intersection m lambda I upon n is same as n. Now this can further be written as intersection of the factor modules m lambda i's by n. Here I varies from 1 to n. This intersection is n. We have taken the family of some modules of the factor module m by n, which is m lambda by n, where lambda belongs to index set, and we have obtained a finite subfamily of this family, which is given by m lambda I by n. Here I varies from 1 to n, and we have shown that the intersection of the members of this subfamily, that is 0 of m by n, and this proves that the factor module m by n is finitely co-generated. So this proves every factor module of module m is finitely co-generated. Now, next we prove the condition 3 implies the condition 1. In the condition 3, we are given that every factor module of m is finitely co-generated. We have to prove that the module m is Artinian. For this, we prove that every descending chain of some modules of m becomes stationary after a finite number of steps. So let us take a descending chain. m1 contains m2, m2 contains m3, and so on. This is a descending chain of some modules of m. Let us take n is the intersection of these mi's. Then intersection of some modules of m, that is again a sum module of m. So n is a sum module of m. Now, because we are given that every factor module of m is finitely co-generated, so to use that condition, we require a family of sum modules of m by n having the 0 intersection. So let us take a family having the members mi by n. This is a family of sum modules of m by n. Now let us find the intersection of the members of this family. Now this intersection can be written as intersection mi's upon n. Now intersection of mi's we have denoted by n. So this becomes n by n, and it is again n. N is the 0 of factor module m by n. So we have proved that this family has 0 intersection for its members. Now because we are given m by n is finitely co-generated, so by definition of finitely co-generated module, there will exist a finite subfamily of the family consisting of the modules mi by n, such that the intersection of members of the subfamily, that will be 0 of m by n. So that finite subfamily we have denoted by the collection consisting of the modules m lambda I by n. Here I varies from 1 to n. So from here we get intersection m lambda I, where I varies from 1 to n. This is n. Now let us take k is minimum of these indexes lambda 1, lambda 2, lambda 3, and so on up to lambda n. Then because we have taken the descending chain of some modules of m, so because k is the minimum of all these indexes, so the module mk, that will be the largest of all the sum modules of m. So mk contains every m lambda I, where I varies from 1 to n. And because for every I varying from 1 to n, m lambda I is contained in mk, so their intersection will also be contained in mk. And also this intersection m lambda I that contains mk. So we can say that the module mk is same as intersection m lambda I varies from 1 to n. So the corresponding factor module will become mk by n. And here we get intersection m lambda I upon n. Now from the equation 3, intersection m lambda I, that is n. So this will become n by n. So from here we can say that the module mk, that is equal to n. Now we have proved the module n is equal to mk. But mk contains mk plus I because we have taken descending chain of submodules of m. Now mk plus I, that contains n because n is the intersection of all mi's. So mk plus I contains n and n is mk. So we have proved mk contains mk plus I and mk plus I contains mk. So we have proved mk is same as mk plus I, and this is true for every I greater than or equal to 0. It means mk is equal to mk plus 1 is equal to mk plus 2 and so on. This proves that every descending chain of submodules of M becomes stationary after a finite number of steps. So by definition, this proves that the module M is Artinian module. So this proves the condition 3 implies the condition 1.